All right. So now, in the past two lectures, we have looked at, electrophilic aromatic substitution. Now we'll switch our attention to carbonyl compounds. And, about 60% of your course of this semester is going to be on this topic. So we'll be looking at how carbonyl compounds react and how we can leverage the versatility of this functional group to make complex molecules. We'll be looking at asymmetric synthesis using this functional group and so on. So, what I'll do in today's lecture, today's topic is that we'll try and see how best we can understand the functional group itself, and then we'll sort of look at molecular orbital picture of this group and how that molecular orbital picture can actually help us understand the various aspects of reactivity. Okay, so we are going to be using hybridization or linear combination of atomic orbitals in terms of description of any compound, but then we'll switch to molecular orbitals when we want to understand certain aspects of stereochemistry and reactivity. So I think you guys should start getting comfortable with both aspects of theory which can be used to explain the experimental outcome. Okay, of course, please do keep in mind that these are just theories, and they are very useful in helping us understand trends and helping us reason out experimental outcomes. Okay, so let's begin this with formaldehyde. I think formaldehyde is one of the simplest compounds, as you can imagine, the carbonyl compound. So I'm just going to draw it out here. So formaldehyde basically has a C double bond O, and it has two hydrogens. Okay, and so if we were to sort of understand the hybridization of this molecule, the carbon here is going to be sp2 hybridized, and the oxygen is also going to be sp2 hybridized, and these two sp2 hybridization helps us understand the geometry of this molecule. For example, the angle is 120 degrees and so on. Okay, but from a bonding standpoint, see, this carbon is first attached to an oxygen through a sigma bond, and of course these two hydrogens through sigma bonds, and then there is this is of course done by the the sp2 carbon and the sp2 oxygen. Okay, and then we have a pi bond. Okay, so the pi bond consists of two of these p orbitals, one on oxygen and one on carbon, and so this bond actually forms the pi bond, which helps us understand the double bond. Okay, so these are things that you already know, but I'm just doing a quick recap so that we can all be on the same page. Okay, so the carbonyl compound has, or the way we understand carbonyl compounds is that the hybridization of the carbon and oxygen is sp2, and there is one sigma bond between carbon and oxygen, which is through the sp2 orbital, and there's one pi bond which is through the p orbitals. Okay, so now let's move on to understanding the aspects of carbon and oxygen. So a typical carbon oxygen single bond is actually 1.43 angstrom. Okay, and a typical carbon oxygen double bond is 1.21 angstrom. Okay, and the electronegativity of the carbon is 2.5, whereas the electronegativity of oxygen is 3.5. Okay, so just keep in mind, electronegativity is the ability of the nucleus to pull electrons towards itself, and so oxygen is obviously more electronegative than carbon, and so that's something that we already know. Okay, so this is just to recap. Okay, now what it also means is that when we start drawing out energy profiles, So let's look at, for example, the molecular orbital picture of carbon. So when we start looking at heteronuclear diatomics, it's important to understand the MO picture of this. So what we need to do is, we need to sort of understand how much energy is required to pull the electron from the outermost filled orbital. Okay, and so the more electronegative the atom, the more difficult it is to pull it, because it's going to be closer to the nucleus. So with this in mind, let's sort of try and picture the various orbitals of carbon. So here is carbon. These are the 2s orbitals, and these are the 2p orbitals. Okay, so carbon, let's start filling it out. So there is 1, 2, and then there's 1 over here. And so this is, as you know, this is the 2px, 2py, and 2pz. Okay, so these are the 3 p orbitals. Okay, and now, for carbon, let's think about what happens when you pump in some energy. And when you do that, what happens is that one of these electrons goes away. That is, it's plugged out from the nucleus. So this is called as the ionization energy. Okay, so this tells us, this is again something that you would have learned many times over in previous courses, but this sort of tells us how close the electron is to the nucleus, and it also helps us understand electronegativity in one way. Okay, now if I have to sort of describe the similar picture for oxygen, what we would do is, since the electronegativity of oxygen is higher, so if I'm going to draw the 2p orbitals for oxygen, so it's going to be something like this. Okay, so here, again, this is the 2s, and here are the 2p orbitals for oxygen, and then I'm just going to fill electrons, 1, 2, 1, 2, 3, and these are the same 2px, 2py, and 2pz. And now if you want to pull an electron out from oxygen, then the kind of energy that you need to spend is actually this. Okay, so when you compare it with carbon, this is the kind of ionization energy of carbon, whereas this is the ionization energy of oxygen. Okay, so now what it tells you is that this kind of a picture helps us understand that it's more challenging to pull an electron out from oxygen compared to carbon. Okay, and so in order to complete this picture with whatever space that I have remaining, I'm just going to draw out the picture for fluorine. So fluorine is over here, right? So again, you have 2 electrons here, 2, 3, 4, 5. Okay, so the electronegativity of fluorine is substantially higher, and the ionization energy is also much higher than that of oxygen and carbon. Okay, so this kind of a framework helps us understand where the molecular orbitals or the atomic orbitals are actually located. And so when we are trying to construct a molecular orbital picture for a double bond, then we need to keep this in mind while doing that. Okay, so for example, when I want to make a pi bond, so I think we are already quite familiar with sigma bonds. I'm not going to spend time with that. But if I want to construct a molecular orbital picture for a carbon-carbon double bond, then what I would do is, my y-axis is energy, and then we have this p orbital for one carbon, and then we have a p orbital for another carbon. So let's say this is a carbon-carbon double bond. So now this is carbon A, and this is carbon B. Okay, and now when these atomic orbitals combine, you have 1 electron each in this atomic orbital, and when these atomic orbitals combine, then you would form a molecular orbital. And this molecular orbital actually has, you get two kinds of molecular orbitals, as you're all familiar with. One is the bonding and the other one is the anti-bonding. And so both these electrons now are going to be spending, or they're going to be populating this bonding molecular orbital over here. And so this is actually the pi bond. And so the bonding molecular orbital, again, as you know, is going to be something like this. So you have, the p orbitals are here, and then when they combine, then they're going to form an orbital such as this, right, between the two nuclei. So this is something that, again, you're quite familiar with. So what you would have is, just to be correct, we need to get the right sign for the atomic orbitals. So this is going to be a pi bond. And now similarly, when you want to form antibonding orbitals, then the way you would combine these antibonding orbitals is in the following manner. So I'm just going to erase this so that we can use the same picture as much as possible. So I'm just going to draw it again here. So this is going to be my bonding orbital, right? And now let's look at the antibonding situation. So when you subtract out, when they combine and form the antibonding orbital, then you're going to get a node that is formed. And so this is the carbon atom, and this is another carbon atom. And so the way in which the antibonding orbitals are going to look like is something like this. Okay, so you have much better pictures in the textbook. And so just to be clear, these are going to be the signs of this bonding orbital. Okay, so this is called as pi star or antibonding orbital. Okay, so very important here to understand that both the carbons contribute equally. Okay, so they are essentially identical in all respects. So they contribute equally to the ensuing molecular orbital. And now let's try to sort of construct a similar picture for the carbonyl C double bond O. Okay, so again, a lot of the reactivity of carbonyl will depend on the pi bond. So let us now only worry about the pi bond. Okay, so let's see, we draw the molecular orbital picture over here. So as I told you earlier, carbon is here and oxygen is here. And again, we need to concern ourselves only with the p orbital, which has one electron each. That is, now we shall assume that both of these p orbitals are going to combine and form a pi bond. And so again, just to remind you, this is the p orbital, and they combine and they give you two molecular orbitals which are denoted as pi and pi star. Okay, so here is the way we understand this. So you're going to combine these two orbitals and produce two molecular orbitals. Okay, so this is the pi and this is the pi star, and so both the electrons are going to be populating the pi bond. And now if you want to understand how this pi bond is going to look like, it's very interesting because the pi star, for example, has a greater contribution from carbon, whereas the pi bond has a much greater contribution from oxygen. Okay, because the character of the pi bond is going to be dictated by the bonding orbital of the pi bond. The pi orbital is going to be influenced greater by oxygen. Okay, so this is something that we can reason out, using trying to measure the polarity of the molecule. And when we draw out carbonyl, typically what we do is when we measure the dipole moment is actually in the direction of the oxygen. So this sort of helps us put this in perspective. Okay, now let's come to the shape of the orbitals. So when you draw carbon and oxygen, if I'm going to study the contribution from oxygen is greater, and so the molecular orbital will look something like this. Okay, there's going to be a much greater contribution from oxygen compared to carbon. Okay, so therefore this is something that we need to understand. All right, and The corollary to this is that you will have a much greater contribution from carbon when it comes to the antibonding orbital. Okay, so let me just erase this so that we can draw it out over here. So here is the carbon oxygen antibonding orbital. So if I have to draw it like this, it would be over here and then over here, and then these are much smaller compared to the carbon-carbon double bond. Okay, so there are two important messages here. Okay, so the pi star has a greater contribution from carbon, whereas the pi has a greater contribution from oxygen. Okay, now one of the meanings of this is that when you want to break the carbon oxygen bond, so what you would do is you would need to fill in the carbon oxygen pi star, which is the antibonding orbital, and therefore the more reactive center here would actually be the carbon. So this molecular orbital picture helps us understand the reactivity of a carbonyl functional group the way we have been used to in terms of the experiments that we do. For example, when we add anything across a double bond, carbonyl double bond, the carbon invariably ends up reacting, and therefore this MO picture helps us put these results in perspective.
Okay, so now given that we have understood how the molecular orbital picture of a carbonyl compound looks like, or a carbonyl functional group looks like, now let's look at some molecular orbital picture of a reaction between an electrophile and a nucleophile. Okay, so as we discussed, so MO theory is very powerful. It helps us understand many aspects of what goes on in a reaction, for example. So if we were to generate an energy profile diagram, so an electrophile, which I'm going to call as E, has a particular energy level such as this, right? And so if you recall, a nucleophile and an electrophile react in the following manner. So E is over here. So there's either a pair of electrons or a negative charge attacking the electrophile. E can be E plus or neutral electrophile, and that's going to give you a new bond between Nu and E, and there's going to be a charge involved here. If Nu minus is there, then it's going to become a neutral species, and you also sometimes have a leaving group and so on and so forth. But essentially, this is the new bond that is actually being formed between the nucleophile and the electrophile. Okay, so bond formation involves a pair of electrons. So coming back to this molecular orbital picture, so if this is energy and this is the electrophile, right? E here denotes an electrophile, right? And now if you want to understand this in terms of how it reacts with a nucleophile, so assume that the nucleophile has to have a pair of electrons. So this is a pair of electrons for the nucleophile, and so which I'm going to denote as Nu, right? And now if we were to construct an MO diagram, so when these two mix, that is this electrophile and nucleophile interact, what's going to happen is you're going to have two new sets of orbitals being formed. One is this and the other one is this, right? So this kind of an interaction actually happens during a bond formation. And now this pair of electrons which was here is now going to form a new molecular orbital, and this molecular orbital is going to basically, this denotes a sigma bond, for example, right? And if this is a sigma bond, and then this becomes sigma star. Okay, so all of this you guys know, so I'm just going to quickly go through this. But the important point to note here is that this energy that is now sort of the gain in stability by loss of energy is what is people understand as a driving force for this reaction. Okay, so the reaction between a nucleophile and an electrophile can result in the formation of a bond, and this bond is going to have energy that is lower in energy. There's going to be stabilization of the electrons during this process. Okay, so therefore for a reaction to occur, electrons have to move, right? And energy differences are important. Now let's think about several situations that can occur. Okay, so situation number one is in your energy profile. So let's say the electrophile is over here and the nucleophile is very stable. There's a huge difference, huge gap in the energy. Okay, so this is the electrophile and this is the nucleophile. So imagine that this is going to be the kind of gap that we're looking at. So the nucleophile, as we discussed, has a pair of electrons, right? And the electrophile is going to be an empty orbital. And now when you draw the molecular orbital picture, you're going to see that it's going to look something like this. Okay, so and therefore your pair of electrons is going to be here, and let's assume that this is a new sigma bond, this is going to be a sigma star, and so on. Okay, so if I look at this picture, I see that there's clearly some stabilization that is being afforded, because if I compare these two energy levels, the sigma molecular orbital is actually lower energy, but this gap is quite small. Okay, so based on this analysis, what we can sort of suggest is that although there's a gain in energy, the gain in energy is quite small, and therefore this may not be as favorable as something which has a greater gain or a greater gain in stability. Okay, so this is not as favorable, and so it may or may not occur. It's probably likely that this kind of a reaction does not occur. Okay, now if you consider the opposite situation, where, or not opposite situation, but another situation where the energy levels are quite close to each other, then when you form new molecular orbitals, then you have a substantial gain in stability. Okay, so therefore the matching of levels of energy between the electrophile and nucleophile are actually going to be quite important. In general, when we're looking at the reaction of two separate, of an electrophile and a nucleophile, what we need to look at is actually something like this. So if I draw the y-axis over here and this is energy, then what we need to really consider is that in the electrophile there would be several energy levels, right? So this is going to be the, let's say, many energy levels, and each of these energy levels is going to have a pair of electrons. Okay, so the pair of electrons I'm going to denote in the following manner. Okay, and there are also going to be many unoccupied orbitals which are going to be higher in energy. Okay, so the most important one is this. Okay, it's called the lowest unoccupied molecular orbital, or LUMO. Okay, so it's important for you to understand this, that there are several orbitals which are vacant and there are several orbitals which are filled. When you're considering from the electrophile standpoint, the most important orbital is the LUMO, which is the lowest unoccupied molecular orbital. Okay, now if I were to construct a similar picture for the nucleophile also may have several occupied orbitals, and there are going to be several other orbitals which are unoccupied, right? So they are free. Okay, so these are all free orbitals, that is, they are vacant. Okay, so again, these are really not important. Okay, not important, right? And in this case, the most important orbital that we need to concern ourselves with is this one, which is the highest occupied molecular orbital. Okay, so this interaction between the highest occupied molecular orbital and the lowest unoccupied molecular orbital is the one that we are always going to be worried about. Okay, so again, just to repeat, these are all filled orbitals, but again, they are not really important. Okay, and in the case of the electrophile, the filled ones are clearly not important, but the unfilled ones with higher energy are also not important. Okay, so this helps us simplify the treatment, and it helps us put a lot of things in perspective, because now we need to concern ourselves only with the lowest unoccupied molecular orbital and the highest occupied molecular orbital. Okay, now coming back to the question of the carbonyl, now let's go back and look at the molecular orbital picture that we have constructed. So we saw that there is a carbon and then there's an oxygen, and that's a sigma bond. and you have, let's say, in case of formaldehyde, you have another couple of sigma bonds with hydrogen here. And we saw that the pi orbital was skewed towards oxygen, and it was looking something like this. Okay, and this is the occupied orbital, which is the pi orbital. So this would be considered the highest occupied molecular orbital. And now if we look at the corresponding LUMO, so I'm just going to draw it here. The LUMO is going to look something like this. So you have electron density is going to be, or the orbital density is going to be higher on the carbon when compared to the oxygen. And that's something that we already reasoned out in the previous lecture. And so these are going to be your pi star orbitals. Okay, so this is important because now the pi star is actually the lowest unoccupied molecular orbital. Okay, so when we are looking at carbonyl chemistry, we invariably are concerned about the lowest unoccupied molecular orbital when we are looking at nucleophilic substitution or addition reactions. And the reason being that when a nucleophile attacks, the nucleophile already has a pair of electrons, and so the nucleophile is looking for unoccupied molecular orbital which it can dump its electrons in, and it can break another bond and form a new bond. Okay, so therefore we need to be concerned in the case of the carbonyl with the lowest unoccupied molecular orbital. Okay, so just to sort of put this back in perspective, so here is your C double bond O, and here's the lowest unoccupied molecular orbital, or the pi star, right? And just to be correct, we have to sort of shade this so that we show the correct sign. And if I have to look at this from the standpoint of geometry, then this is going to be one of the hydrogens, and this is going to be the other hydrogen. Okay, so therefore the C double bond O is in the plane, right? And this pi star orbital is over here. Okay, so therefore when this attacks, when a nucleophile attacks, the nucleophile actually approaches from here, right? And it starts to bond with the pi star orbital, and this results in the breaking of the carbon oxygen, the pi bond, and you actually end up with a new bond between the carbon and oxygen. Okay, so this is how we would understand the reaction or nucleophilic addition towards a carbonyl compound. Okay, so just to repeat, in order to form a bond here, we need to break, or we need to add electrons to an antibonding orbital or the pi star orbital. And once the pi star is actually filled, that results in breaking of the pi bond, and then the electrons are actually moved towards the oxygen. Okay, so this is how we try and understand how nucleophilic addition happens on a carbonyl compound.